All right, so in this video, we're going to derive the D6d character table. And as always, the first part of these videos is coming up with all the symmetry operations in the point group and then organizing into the classes. So, of course, we're going to have the identity point group. A lot of times we use an example molecule um, to do that. I don't have an image of the example molecule, but one example molecule would be a staggered bis chromium benzene in the staggered conformation. Basically, what you need to have this symmetry is you need to have a hexagon um, on one face. Since central atom, this is going to be the most common way that this is going to work. And then you're going to have some other hexagon that's staggered from that. So you get this off axis, because if they're eclipsed, you'll have D6H symmetry instead. But as it turns out, for these DND point groups, it's pretty easy just to come up with the point group operations, thinking about the very first sorts of symmetry that you're going to have. Of course, you're going to have a C6, right? And that's going to be defined as our z-axis when we do this, but we're gonna have a C6, and you're also gonna have an S12. You look at these D and D point groups. You always have an S that's 2 times the n value of the Cn, and that's because you have these off-axis cases here where one of these atoms then can rotate not 60 degrees but 30 degrees now, and then be flipped down, right? An S12, remember, is a C12 followed by sigma H. So flip down where it lines up into the other atom of the hexagon that is offset by 30 degrees. So you always have that sort of situation here. So if we have the S12 and the C6, and of course, we're going to have the n perpendicular C2s. We always have n perpendicular C2s. This is a D and D general class of point groups. So specifically, we're D6d, and so that means we're going to have 6 perpendicular C2s. So in a hexagon situation with the 2 hexagons and the central atom, these C2s are going to be flipping these hexagons and turning one hexagon into the other hexagon. And then we're also going to have and so those are all going to behave very similarly. So I'm just going to go ahead and put them, I'll use in red because we're talking about a class now. I'm going to put them into the same classes. Our perpendicular C2s almost always in point groups go in the same class. And then we'll also have 6 sigma Ds. And of course they're Ds because we're in a D point group. But these are Ds mirror planes, dihedral mirror planes, which mean they bisect the perpendicular C2s. So we can even come up with those without really visualizing them too much, at least at this stage. And then those are going to all be in the same classes, similar to one another. And then at this point, we can say, certainly identity is always in its own class, so drop the hat notation. Remember, hat notation means it's an operation. If I don't have the hat notation, it means it's a class. And then I have the C6 and the S12, and basically we're going to run these operations multiple times and use them to generate other operations. So I'm just going to draw out a hexagon here just to help us visualize some things as we talk about this. But we can have a C6, we can run the C6 twice. That's going to be equal to a C3. We can run the C6 3 times. That's going to be equal to a C2. And we can run the C6 4 times. That's going to be equal to a C3 twice. And we can run a C6 5 times, and that's just going to be all that is. And then a C6 6 times, we can't do that. That's a 360-degree rotation, which is equal to identity, which we already have. So that's redundant. So we have these different operations. Now we need to group them into classes. And if you think about it, the C6 5 and the C6 1 time, those are going to go into one class, and we're going to call this a 2C6 class. And the reason why those go into one class is because if you do a C6 60-degree rotation, takes this atom to that atom, But if you do a C 5 times, you go 1, 2, 3, 4, 5, it's the same as doing the opposite direction of C6. So C5 and C6 5 times and C6 1 times are equivalent if you just define your which way you're rotating differently. So it's sort of arbitrary whether or not you do a C6 or C6 5. And so in this way, C6 and C6 5 are mathematically very similar, and so we can put them into the same class. And the same logic applies to some other examples here, which are C6 twice and C3, and C6 4 times or C3 twice. Okay, those are going to go into the same class. So those are two C3s, and very similar logic here. If we do a C3, so we do a 120-degree rotation, we go to there. Or if we do a 240-degree rotation, we go to there. But if we do rotation the other direction, 120 degrees, we do equivalent as a C3 twice. So same exact logic, those go in the same class. And that leaves us with C2, which is the 180-degree rotation along this perpendicular principal rotation axis, not to be confused with these perpendicular C2s. That one is its own class. So we'll just write C2s, and I drop the hats. One C2, or just C2, you can drop the prefix of 1. Okay, and so now let's think about, so we've done everything we can with the S, with the C6 operation. Let's run the S12 operation multiple times. So I have the S12 2 times. What does that give us? Well, that's, remember, S12 1 time is a C12, so a 30-degree rotation, followed by sigma H. S12 12 times is then a C12 2 times, which is equal to C6, followed by sigma H 2 times. Well, sigma H, you do, it's perpendicular sigma H, right? So again, you have those two hexagons that are offset from one another. Sorry, I drew a pentagon there, but you get the idea. And you have a mirror plane in between these two. And so you're flipping the top to the bottom and the bottom to the top. And so if you go and do one of these mirror planes twice, top goes to bottom and bottom goes to top, well, you ended up doing nothing. Top just stayed at top and bottom just stayed at top. So running a mirror plane, a perpendicular mirror plane 2 times is the same thing as just identity doing nothing. And in fact, any even amount of flips is just identity. And so this term goes away. It's like multiplying by 1. Then you have the C12 2 times. Well, that is doing a 30-degree rotation twice, which is equal to a 60-degree rotation. So we already have a C6. It's in the 2C6 class. So S12 3 times didn't give us anything new. What about S12 3 times? S12 3 times gives us a C12 3 times, followed by a sigma H 3 times. Well, C12 3 times is equal to a 90-degree rotation. So that's a C4. And the sigma H 3 times is just equal to sigma H, right? Because it's the odd number flips top to bottom, bottom to top, top to bottom. It's the same as just doing top to bottom. And this, by definition, is equal to an S4. So we actually have a new operation here, S4, that we uncovered. So far we have S12 and we have an S4. Maybe we'll use a different color here for the S12. All right, and what if we do S12 4 times? Well, it's even number. This isn't going to give us anything unique. This is going to be a C12 4 times, followed by sigma H 4 times. Sigma H 4 times is even number flips, does nothing. C12 4 times is equal to C3. We already have a C3 right here. We already counted for that. S12 5 times. S12 5 times ends up being unique. It's a C12 5 times, followed by sigma H 5 times, which a sigma H 5 times with an odd number of flips is just a sigma H. So it's a C12 5 times followed by a sigma H. That's a unique operation. So I'm going to give that another color here. And I'm using these colors of how they actually end up grouping into classes. And we'll talk about why they're in those classes. S12 6 times equals C12 6 times followed by sigma H 6 times. That's a C2, and nothing else. Sigma H 6 times does nothing, and we already have a C2 over here. S12 7 times. S12 7 times is equal to C12 7 times, followed by sigma H 7 times. Odd number of flips, this is C12 7 times, followed by sigma H. And this indeed is unique. And it turns out this is the same as a S12 5 times. So I'm going to use green here, and those are going to go into the same class. So our class here is going to be called 2S12 5 times. Why is that? Well, if we have our hexagon here, and we start at one atom, and we do, now we're doing 12s, right? So go 1, 2, 3, 4, 5, or we do 1, 2, 3, 4, 5, 6, 7. That red line is the same as we do 5, 1, 2, 3, 4, 5. We got to the same spot. So S12 7 times is equal to S12 5 times if you just flip the counterclockwise versus clockwise. So they're sort of arbitrary. So mathematically, they're very similar. So they go in the same class. Keep marching along here. We can do it. Think about S12 8 times. Even numbers don't generate anything new. That gets us sigma H 8 times, which goes away. And then we get what basically is a C3 twice, which we already have. S12 9 times. That is a C12 9 times, followed by sigma H 9 times. And a C12 9 times, that is something that we haven't talked about yet before. That's well, least common denominator here, divide by 3. So it's a C4 3 times, followed by a sigma H. Okay? And a sigma H is the same as a sigma H 3 times. And so this is actually just equal to the definition of an S4 3 times. And so an S4 3 times and an S4 are the same. And so in the same class, counterclockwise versus clockwise, just like the logic we did here. And so those go into their own class, 2S4. We have S12 10 times. That is equal to C12 10 times, followed by a sigma H 10 times. It's equal to a C6 5 times, and sigma H is an even number of flips, so it doesn't do anything. And so very lastly, running out of room here, but we have, actually, let's do it up here. We have S12 11 times. S12 12 times, I think you can see its identity. S12 11 times, it's going to be C12 11 times, followed by sigma H 11 times. It's an odd number of flips, so it's C12 11 times, followed by a flip. That is very similar to an S12 by itself. And so indeed, these two, S12 11 times and F12 1 time, go in the same class, which is kind of called 2S12. Because an S12 11 times versus an S12, they're identical, just they're identical if you redefine whether or not you're doing counterclockwise, clockwise rotation. So mathematically, they are pretty much the same. And so that brings us to actually completion here. Those are all the different operations that we have. So in total, we have we have 1, 2, 3, 4, 5, 6, 7, 8, 9 classes. Nine classes, that's right. And we have a total of looks like 24 operations. Okay, let's see if we do that right. Because we have one identity, we have one C2, so that gets us to 2. We have two C3s, gets us to 4. Two C6s gets us to 6. Two S12-5s, it gets us to 10. Two S4s gets us to 12. And then we have 12 of these perpendicular C2s and those mirror planes. Okay. So now in the next video, what we'll do is we'll be able to make our character table starting from these 9 different symmetry classes and all operations that we derive. We'll actually derive the irreducible representations. Of course, we're going to have 9 irreducible representations because we have 9 classes.